All right, so now we're going to compute other volumes. These ones are going to be called volumes of revolution. So let's start talking about our solids of revolution, rather. Let's start talking about how in the world do we form them, or how do we start with them. So let's say you have a curve, our favorite y equals x squared, if you will. Let's write that. I'm going to just write the positive side. I'm not going to write the whole parabola, draw the whole parabola. Although this thing did more or less of a quarter circle, but that's okay. Gives us an idea. So we're going to grab that curve and we're going to spin it around the x-axis. So you're going to grab it and go around. And in fact, I misspoke. That would form a surface if you just grab the curve. You're going to grab the whole area under that curve. And you're going to spin it around the axis. And that's going to form this sort of solid. And this is going to be completely solid here. So it's going to be a, what would you call that? I don't know, like a trumpet, but it's going to be solid. It's not going to be, so not quite like a trumpet because it would be hollow, but it's solid. So that would be called a solid of revolution. So you form them in that way. So let's see what happens if on the other hand, let's delete this. If on the other hand, we would rotate this around the y-axis. So let's not grab the area that, well, we can grab whichever area we want, really. So let's grab that area here again, but now let's rotate it around here. What you would end up with, well, you would have, let me try to draw the same, more or less the same curve over here. Sort of, should be symmetric, because you're gonna rotate it around this axis, and what you would obtain is going to be a kind of like a bowl that is hollow inside. So right here you would be rotating around here, but this part up here would be hollow. And so those are going to be called solids of revolution. Whenever you have an area and you rotate them around either axis or around any line, we're going to do only vertical and horizontal lines. We're not going to go crazy and grab a slant line and rotate around that. We're not going to do that. We're just going to do vertical and horizontal lines. But those are going to be called solids of revolution. So why not? Let's compute the volume of this thing. Let's say that we're going from 0 to 2. Change color. So I'm going to go here from 0 to 2, grabbing this area, and I'm rotating it around. And let's see how we can compute that volume that we obtain. So we're going to kind of follow the same idea as before, where you cut things in terms of rectangles. And you're going to rotate it around. Unfortunately, I'm going to start with a shell, and that's the one that people have a bit of a difficulty with. But, here we are. So we're going to do it with a shell first. These names of the methods really mean nothing. You'll see that some people will call them shells. Some people will call them discs and washers. And the reality is those are just names. The ideas are the same. And the idea really is you're going to grab a rectangle, you're going to spin it around, and you're going to compute the volume of the object that you obtain. And then you're going to be adding through the entirety of your area. So from 0 to 2. So I'm getting this volume here that I want to pull out, and I want to draw it here. So that's what people will call a shell. So that is going to be this. Obviously, this one looks much better than this one, but it's just the fact that I'm drawing that there. So let's find out some dimensions for this shell. Notice that this right here, this height is going to be the y coordinate of my point, whichever the point is. Now x is going to be located from here all the way to here. That's going to be my x. And that turns out to be the radius of this shell. Maybe put it up here. It's less busy. That turns out to be an x. And then the width that I'm taking, that width is going to be called dx. And why dx is because I'm picking it on the x-axis. If I would pick a shell over here or a rectangle over here, that would be a dy. But it's going to be a dx because I'm picking it on my x-axis. That's where the small rectangle that I rotated around, that's the width of it, is a dx. All right. So then we want to compute the volume as before. We want to compute dv is going to be, well, we had to figure it out here, what that's going to be. And to do that, and so the question is that, once we have that, we can integrate, in this case, from 0 to 2, and that would give us our volume. Great. However, we need to find that dv. I know that it's going to be related to an area times the dx, but how do you compute the volume of this cylinder? Is not solid, so you cannot use the formula of a cylinder, which would be the pi r squared h. That's not going to work. But what you're going to do, or what I do here, is we're going to make a cut here. I cut it out, and I'm going to spread it out wide. So when I cut that cylinder and I spread it out, I get a little solid. The width is dx, as we said, so that dx is still the width of the, so when you grab it, you turn the circle, cut it, and then you stretch it out like you would be cutting a toilet paper roll, and you're opening it up. That's what you're ending up with. And so the height is going to be here now. So that height here becomes that. And this here, what is it going to be? Well, it's going to be the circumference of this circle. The circumference of that circle, remember, the circumference is 2 pi r, or the perimeter is 2 pi r. And in that case, then it would be 2 pi, the radius is x, 2 pi x. So the dv for this thing is going to be 2 pi x times y dx. Well, we have to substitute in. So this is just base, if you will, height times the thickness, 2 pi xy times dx. Just put in them all. All right, and now what we do then is we figure out what y is. But remember, y is given to us as a x squared. So dv equals 2 pi x, and instead of y, x squared dx. And now we're in position to, I'm going to change color again, to write our integral. V is going to be the integral from 0 to 2 of 2 pi x times x squared is x cubed dx. Now we can integrate 2 pi, this is going to be x to the 4th over 4, between 0 and 2. All right, and now it's just a matter of plugging this in. I could have simplified here a little bit. At the end is going to be 2 to the 4, which is 16. Divided by 4 is 4 times 2, 8. That's going to be 8 pi minus 0, but that's just going to be 8 pi by computing that integral. And that's going to give us, if you want to be precise, it would be units cubed, because you're now computing a volume for that bowl that we computed. All right, I think this video has gotten a little bit longer. Please let me know in the comments if the way we construct the solids of revolution makes sense. If not, I can record another video. Perhaps I can use computer tools or aids to show you visually how it works. I can do that if it's not clear. Now, the method of solving, I'm going to solve a large number of examples for this until it's very clear, because I know that shell method, which is called, this is what it's called, and the next one, the other ones that we call disk and washer method, they all are the same idea. You just end up with different figures. So I don't like to call them methods. I like to just explain how it works. but then again, in the book you'll see it with names attached to them. So I'm gonna do more videos of that, but the intention of this video firstly is just to explain how these solids are created, how they're generated. So let me know in the comments if it's making sense or not, and if not, just move on to the next video.